lecture 36 of our series on numerical methods in civil engineering, we will wind up our discussion on spline functions, which we started last time, and then move on to a discussion on orthogonal basis functions for solving partial differential equations. Let us recall that spline functions are another set of basis functions which can be used for constructing an interpolant. Right, this technique uses a combination of spline functions, right, and the idea of spline functions we found stems from engineering design, where designers often used an elastic ruler known as a spline to pass through a given set of points, and people found that this spline was nothing but a series of cubics defined over the intervals of interest. If I have several grid points and I know the function values at those grid points, the final fit was obtained by considering cubic functions, cubic polynomials over each of those intervals, and then ensuring continuity in the function values as well as in the derivatives across the element boundaries, not only the first derivative but also the second derivative in case of cubic splines. And these basis functions are independent, right? So the different cubic polynomials, so at different basis functions in different intervals. Only difference with the type of basis functions that we were considering earlier, these basis functions have local support, right? So they are defined over small intervals, right, not over the entire domain, right? And the spline function is a combination of these polynomials. And the power and flexibility of spline functions stem from their ability to have different polynomial representations in different intervals, while at the same, so that's why you can basically modify a complicated function with lot of variation, right, using different functions in different intervals. You do not have to use a very high order. The other alternative is to use a very high order polynomial, right, throughout the interval, but that is no longer required. So you use a relatively low order polynomial, in case of cubic splines a cubic polynomial over these intervals, and they are different over each interval. And we also found that the cubic spline has this representation. So if I define the spline over the interval xi minus 1 xi and denoted by qi, so I denoting this interval I minus 1 I, then that cubic spline has the following representation, where t is nothing but x minus xi minus 1 by hi. So it is the parameter over that interval xi minus 1 xi, right, for all x belonging to that interval. Hi is just the size of the interval, di is the slope, right, slope yi minus 1 by hi, and the ki's in this equation, in this expression for the cubic polynomial, are obtained by solving this tri-diagonal system of equations. And towards the end of the last class I told you that these ki's are nothing but the second derivatives of this qi, right. And this system is so what we found at the end of last class was that given this representation of q, given this representation of the cubic polynomial, it satisfies continuity in the function values and continuity in the first derivatives by construction, right. The way it is constructed, it always satisfies continuity at the ends of the interval, both in the function values as well as in the derivatives. But in order to ensure that the second derivative is also continuous across the intervals, the ki's have to satisfy equations of this sort, right. And you can see that this system, so there are m minus 1 equations, but there are m plus 1 ki's, right. So because of that we need two other constraint equations which we are going to talk about later. And from, as I said, that given the definition of qi, continuity in the function values is satisfied by construction. So for instance, in xi minus 1 xi, if x is equal to xi, this means t is equal to 1. So t goes from 0 to 1 throughout the interval. So if I am looking at the right hand point at x is equal to xi, right, at this point, then t is equal to 1. If I substitute t equal to 1 in this equation, I find that this gives me qi xi is equal to yi, right. Similarly, if I am looking at the interval xi plus 1, the adjacent interval to the right, in that interval if x is equal to xi, t must be equal to 0, right, because it is at the starting point of the interval, the left hand starting point. So t is equal to 0. If I substitute t is equal to 0 at that interval in this equation and evaluate it at xi, right, instead of qi I will use qi plus 1 and evaluate it at xi, I am also going to get yi. That means what? The function value is qi xi is equal to qi plus 1 xi. That means it is continuous at the interval. The function values are continuous at the interval boundaries. To prove continuity in the derivatives, we use the following result: dt dx is equal to 1 by hi, and try to find the derivative of this expression, right. I try to find the derivative of that expression. So I find qi prime x instead of, so now t is the independent variable, so dqi dx I want to find, but then I have used this intermediate parameter t, so I use dqi dt dx is equal to, from this expression dt dx is equal to 1 by hi. So I have 1 by hi times dq dx ddt of this expression, right. I have ddt of that expression, so I get that. And then if I want to evaluate qi prime, so I look at the interval xi minus 1 xi, right, and I want to evaluate qi prime at xi minus 1. Qi prime means the derivative, this function is cubic function with respect to this interval xi minus 1 xi, right, and I am going to evaluate it at xi minus 1. So that means I evaluate it at t is equal to 0, because the interval is xi minus 1 xi, t is equal to 0 at xi minus 1, t is equal to 1 at xi. So I evaluate this at t is equal to 0. If I do that, I get ki minus 1, right. So I just substitute t is equal to 0 in this expression, right. Then if I want to evaluate qi prime at xi, so I am using the same interval, right, xi minus 1 xi, and I am evaluating the derivative at xi. That means I am evaluating the derivative at t is equal to 1. If I do that, I substitute t equal to 1 in this expression, I get is equal to qi equal to ki, right. Then I use the fact that since qi prime at x minus 1 is equal to ki minus 1, if I want to evaluate, if I replace I by I plus 1, I can get q prime at I plus 1, just replacing I by I plus 1 in this expression, xi is equal to ki. But we have already found that qi prime at xi is equal to ki. So that means for the interval xi minus 1 xi, if I evaluate the derivative at the right hand point, I get ki. For the interval xi plus 1, if I evaluate the derivative at the left hand end, right, I get ki. That means that the derivatives are equal at the boundaries, and therefore we have continuity in the derivative as well. Thus by construction qi, the construction qi has continuous function values and derivatives of the spline function at the interval boundaries. But in addition, the second derivatives of the spline also have to be continuous across the interval boundaries. That means that this condition has to be satisfied. At the end of interval xi minus 1 xi, the second derivative must be equal to the second derivative at the beginning of the interval xi plus 1, which is this condition, right. And then if I impose that condition on this equation, if I use this equation, I impose that condition that the second derivatives are continuous at the interval boundaries on this equation, I get these equations right here, this trigonal system, right. And then I need to solve that tridiagonal system. but as I said, we need 2 additional equations, but because there are fewer equations than the number of unknowns. So we need to solve that system with constraints, and the constraints we use require that the spline be a straight line outside the interval, right. If it's a straight line, that means its curvature got to be 0. Curvature got to be 0, that means that the second derivative got to be 0. So S double prime x is equal to 0 for x lesser than or equal to a and x lesser than or equal to b, right. So if so that means we are looking at the first interval and the last interval, right. So if q1x is the cubic in the first interval and qmx is the cubic in the last interval, this means that q1 double prime at a must be equal to qm double prime at b, because qm refers to the last interval, and both must be equal to 0, right. Both must, you can see these are splines, a straight line outside that interval, right. What happens, so these conditions give me these 2 additional equations, right. You can see that the first equation involves k0 and k1 because it refers to the first interval. The last equation involves km minus 1 km because it refers to the last interval, and these 2 are the additional constraints. Now I have m plus 1 equations for my m plus 1 constraints. I can solve them, I get my k values, and once I know my k values, I can fit my spline throughout the interval, right. So it's not expensive because the system, as we have seen earlier, is a tridiagonal system. Solving a tridiagonal system is not that hard, right. Now we have said that we are going to use a cubic spline to exactly fit the function values, but suppose in that interval, but suppose my actual function doesn't have 0 curvature at the ends. What then? My spline has got 0 curvature at the ends. What happens if my actual function doesn't have 0 curvature at the ends? In that case, there is some loss of accuracy. The fit is not as good, right. So the good fit is still obtained at the center of the interval, but towards the end of the interval the errors are somewhat larger, right. So near the center of the interval, the error is of the order of h to the power 4. So you can see the error is really it is the order of accuracy is really high, right. So h to the power 4, right. As you reduce the size, the error goes down like quintically, right, while the error near the boundaries are somewhat larger, right, if the real function doesn't have 0 curvature at the ends of the interval. So with that, I want to draw a close to my discussion of spline functions. These are very useful functions, right, because they have this, they give me very good accuracy. Like, recall, if I have a polynomial with a lot of maxima and minima, right, with a lot of maxima and minima, in order to if I have a function with a lot of maxima and minima, in order to have a polynomial maxima and minima in a certain interval, right, lots of stationary points within an interval, if I have to use a polynomial to fit that function, it has to be a very high order polynomial. And as we have seen with the high order polynomial, if you have equidistant grid, we are going to get erratic behavior, ill conditioning, and so poor fit at the ends of the interval. So the alternative to that, we found one alternative was to use Chebyshev interpolation. Other alternative is to use splines, right, splines, where you use a relatively lower order polynomial. You do not have to use a very high order polynomial, use a relatively lower order polynomial, fit it across that interval, which assumes different forms within each sub interval, right, same order but different form, and then you can get a good fit even using a equidistant grid. Okay. So with that, we are ready. We have talked enough about orthogonal basis functions. So we want to use these basis functions for solving our partial differential equations, and we will see that this idea of orthogonal basis functions is the foundation of almost all widely used methods used for the numerical solution of partial differential equations, including the finite element method, right. So let's do that. So, notion of linearly independent basis functions for a function space is widely used. It is the foundation of techniques such as the Galerkin method, the collocation method, the weighted residual method such as the finite element method for the solution of ordinary and partial differential equations. Suppose we have a linear partial differential equation denoted by the action of a linear operator L, which we have encountered earlier, on the variable u, so Lu. Also suppose that u belongs to the domain D, where D is a subset of Rk. Rk is the kth dimensional Euclidean space. So, 2-dimensional Euclidean space or 3-dimensional Euclidean space. In D, Lu is equal to f. So, this linear operator operating on u is equal to f, a given function f, suppose. And on the boundary of D, so on del D, which is the boundary of D, let us suppose that u satisfies another relationship, again defined by another linear operator, in this case L bar, right. So, L bar u is equal to g on del D. So, within the domain D, Lu is equal to f. On the boundaries of that domain, L bar u is equal to g. So, examples can include any of the canonical partial differential equations we encountered earlier. For example, Laplace's equation in a 2D domain, right. So, del to u del x square del to u del y square is equal to f of x y on D, which is a subset of the 2-dimensional Euclidean space, and u is equal to 0 on del D. In this case, L obviously is del square x square by del square plus del square y square, Laplacian operator in 2D space, while L bar is the identity operator, because L bar u is equal to u, right. So, L bar is the identity operator, and g in this case is equal to 0, right, it is equal to 0. So, the general linear problem A, if we define the general linear problem A to be Lu is equal to f in D and L bar u is equal to g on del D, can be simplified somewhat if we can solve two independent problems. What are the two independent problems? Two independent problems are Lu1 is equal to f in D and L bar u1 is equal to 0 on D. So, now instead of solving this problem, we solve, instead of solving this problem, we solve the homogeneous problem. First, the homogeneous boundary condition, right. So, Lu1 is equal to f in D, but L bar u1 is equal to 0 on del D, right. Same problem with homogeneous boundary conditions. That is the first part. The second problem is Lu2 is equal to 0. So, within the domain Lu2 is equal to 0, the boundaries L bar u2 is equal to g. So, it is the complementary problem, right. So, this the problem B and its complementary problem C, right. If we solve B and C, then we can always obtain a solution for A as u is equal to u1 plus u2 as the sum of these two solutions. Why? Because this operator L is a linear operator. So, Lu1 plus L2 is equal to Lu1 plus L2, which is going to be f in D, because Lu2 is equal to 0 in T, Lu1 is equal to f in D. So, Lu1 plus L2 is going to be f in D, while L bar u1 plus L2 plus u2, again taking advantage of linearity, is going to be L bar u1 plus L bar u2. This is equal to 0, that is equal to g. So, this whole thing u1 plus u2 satisfies my original problem. So, if I can solve the problems B and C, then I can always construct solutions to my original problem A by adding those two solutions together, taking advantage of the linearity of the operator. Recall that one of the analytical techniques we looked at for solving second order linear partial differential equations was the method of eigenfunctions, right. In this method, we found we solved the eigenvalue problem. So, initially we solved this problem, Lu is equal to minus lambda u, subject to homogeneous boundary conditions, and we found that the solution, if this operator was self-adjoint, then the eigenfunctions formed an orthogonal basis for my solution space of this function. So, it formed an orthogonal basis for the solution space. So, any solution could be constructed by taking a linear combination of my eigenfunctions that we have seen in great detail earlier. We have used that technique for solving the wave equation, the diffusion equation, and so on and so forth. However, the operators L and L bar are often too complicated. They are never, if they are not as simple as my Laplacian, right, if they are complicated, or if my problem domain geometry is really horrendous, right, it is very complicated, then it is not possible to solve this problem analytically to get the eigenfunctions. So, then my analytical approach breaks down. I can no longer solve my eigenfunctions and can no longer construct my solution using those eigenfunctions, right. Then what do I do? Well, in such a situation it is not possible to obtain a solution for A in terms of eigenfunctions. However, in that case, given an appropriate set of linearly independent basis functions, right, we attempt to construct approximate numerical solutions U tilde, taking advantage of the fact that any U tilde belonging to the n dimensional function space spanned by psi by these basis functions can be represented as a linear combination of the basis functions. Now, there are a number of methods which can be used to construct the solutions in this manner. These methods differ first on the choice of the basis functions, first on the choice, no, not just the basis, it depends on the choice of the space, right, choice of the function space, right, n dimensional function space spanned by psi. A particular method may require the function space to be the space of functions with continuous first derivatives. Another method might require the function space to be the space of continuous functions, right, it only requires continuity in the function values, not in the derivatives, right. In addition, the methods may differ in the way the coefficients are evaluated. The coefficients C0, C1, C2, C3, Cn, the way I form my coefficients. So, it depends on the function space, on which function space I choose to construct my approximate solution, right. It depends on the, so once I know my function space, probably the basis functions are known, right. So, then it depends on the basis functions, right, and then finally it depends on the coefficients, right, it depends on the coefficients, right. Since the problem A can be easily solved if B and C can be solved, we will consider approximate solutions to the problem B, to this problem, right. We will consider approximate solutions to the problem B. So, if we can solve B, we can easily solve C as well. So, we will only consider solutions of B. The same methods can be used to solve C, and once we have solved B and C, we can construct solutions to A. To solve B, we use the n dimensional function space Hn such that U tilde obtained as above also satisfies. So, U tilde obtained as above, I mean U tilde obtained like this, right. Oh, so that is a typo. So, it is C1, psi1, C2, psi2, Cn, psi-n, right. So, if I construct U tilde like this, right, I construct, but U tilde also has to satisfy this condition, right. So, U tilde belongs to the function space, is constructed by taking a linear combination of the basis functions spanning the function space Hn, which I am denoting as psi 0, psi 1 through psi n, but U tilde in addition it satisfies the boundary condition for my problem B, which is L bar U tilde is equal to 0 for all U tilde belonging to Hn, right. So, Hn may for instance comprise polynomials of order 0 to n multiplied by some appropriate function in order to satisfy the boundary conditions, right. The members of Hn, which we have already seen, are denoted by psi j, j is equal to 1 to n. To solve L U tilde is approximately equal to f, with U tilde is equal to C1 psi 1 C2 psi 2 through Cn psi n, right. We have to satisfy this equation. C1 L psi 1 plus C2 L psi 2 plus Cn L psi n is approximately equal to f. The criterion, this is very important, the criterion used to enforce the condition that the f is indeed approximately equal to sigma Ci L psi I determines the nature of the solution method. As we will see, the least squares approximation is different from Galerkin. Why? Because the criteria used to enforce this condition is different. So, the criteria defines the method. The criteria used to enforce this condition that L u tilde is indeed approximately equal to f determines the approximate solution method, right. If least squares minimization is used, this condition is enforced by requiring norm of f minus sigma I equal to 1 to n Ci L psi I be a minimum, right. Only then it is the best solution, right, it is a minimum. If the L2 norm is chosen for the least squares minimization, that means this square which is in the L2 norm, this is equal to the inner product, right, norm square is equal to the inner product. So, this is equal to f minus sigma I equal to 1 to n Ci L psi I, f minus this inner product must be a minimum. And we have seen from our discussion of linearly independent polynomials that in order to minimize the approximation error in the L2 norm, this has to be the residual f minus sigma I equal to 1 Ci L psi I has got to be orthogonal to each L psi I, right, because I am taking the linear combination of the L psi I's to construct my approximate solution. My approximate solution is equal to C1 L psi 1 plus C2 L psi 2, right. This must be equal to f, right. So, f minus L, this one must be equal to these building blocks L psi 1. My approximate solution is actually C1 psi 1 and so on and so forth, but my this is approximately equal to a linear combination of these, right. And we have seen that in the least squares method the residual must be equal to these must be orthogonal to these quantities, right, L psi 1, right, L psi 1, L psi 2, L psi n, right. It must be orthogonal to the building blocks of my of what is approximately equal to f, right, the quantity which is approximately equal to f, right. Is that clear? So, earlier we were not looking at differential equations. So, there was no L there, right, there was no L there, we are just trying to fit a function, but now there is this, we are solving a partial differential equation. So, now there is this operator L, right. So, the difference must be orthogonal to L psi 1, L psi 2, L psi 3 and L psi n, right. So, this must be orthogonal to that for all psi j is equal to 1 through n, and this requires, if I just expand this inner product out, that means f L psi j must be equal to sigma Ci L psi j L psi j psi I psi j sigma Ci L psi I L psi j, which again if I pull out the constant I get that, right. So, denoting these Ci's as the vector C, vector f L psi 1, f L psi 2 with the scalar components of f being L psi 1 inner product f, L psi 2 inner product f and so on. So, I get a vector here, I denote that as a vector, and here I get a matrix whose components are these dot products, right. So, the first component is L psi 1 inner not dot products or inner product. So, L psi 1 L psi 1, second component is L psi 1 L psi 2, third component is L psi 1 L psi 3 and so on and so forth. So, then I get a system which is equal to A C is equal to F, right, A C is equal to F, where this is my A, right. So, if I know my basis functions I can evaluate the components of A, right, because this is nothing but L psi 1 L psi 1 inner product of L psi 1 with itself. This is L psi 1 inner product L psi 2. So, I know the components of A, I know the right hand side because my function f is known, my L psi 1, L psi 2, L psi 3 are known. So, my right hand side is also known. So, then I can solve for my C's and I get my solution. We finally get the matrix vector equation AC is equal to F. Solving the above system yields C1, C2 through Cm, and once I get C1, C2 through Cm, I get U tilde is equal to sigma Ci psi I, right. So, that is my least squares method. Then if instead of evaluating these inner products, so these are inner products, right. So, that means it involves evaluating an integral. So, it is continuous, assuming that the functions are continuous, right, and I am evaluating that inner product over my domain of interest, right. So, if instead of evaluating that integral, that is treating it as a continuous basis function, the psi i's as continuous basis functions, if I treat it as a discrete problem, right, and I start evaluating the inner products at discrete points, suppose m points in the domain, we have what is known as the collocation method, right. So, in that case my AJI I am going to evaluate it as a sum, and that sum is going to involve these sort of L operating on psi j evaluated at xk. So, I am evaluating my basis functions at discrete points, right, at x1, x2, x3 to xm, right. So, L psi j evaluated at xk times L psi I evaluated at xk, and then I sum it over, right, k is equal to 1 to m. I think that I have made a mistake here, right, there is no sum here, right. So, AJI is equal to L psi j L psi I xk, there is no sum here, sorry, there is no sum here. So, each of those components are evaluated there, right, or is there, let me see, no, there is a sum. I apologize again, there is a sum because this involves this, I am just evaluating that integral, but I am evaluating that integral at a discrete set of points, right. So, there is a sum. I'm sorry for the confusion. So, the only difference is that instead of evaluating that inner product, right, as an integral, I am evaluating it as a sum, right. So, I am evaluating these functions, these basis functions at each of my grid points and then summing them up to get the, so to get AJI I am evaluating psi j at k is equal to 1, psi I at k x1, right, then my L psi j at x1, L psi I at x1, then I am adding to it L psi j at x2 times L psi I at x2 and so on and so forth, right. So, it is a sum, I am sorry for the confusion, right, and then Fj, to evaluate the Fj I similarly I convert it into a sum. So, again I evaluate L psi j at x1 times F evaluated at x1, add to that L psi j evaluated at x2 times F evaluated at x2 and so on and so forth, and I get my Fj, right, the contribution to F after sort of taking the projection with psi j, right. So, this allows me to evaluate my coefficient matrix as well as my right hand side in a discrete fashion without performing the integration, right, and this gives me what is known as the collocation method, because as we will see in the collocation method, typically these psi j's are delta functions, right, these psi j's are delta functions. So, basically they are the delta function, so that means that each of these basis functions are 1, suppose psi j is 1 at x1 but 0 everywhere else, right, psi 2 is 1 at x2 but 0 everywhere else, right, so and so on. So, if these are delta functions, that then in this summation only, so so it becomes a lot simpler, right, if once they are delta functions, right, is that clear? So, the number of contributions becomes much smaller in that summation. and actually if they are delta functions, then we are going to get this whole thing becomes uncoupled, right. So my coefficient matrix is actually going to become a diagonal matrix. See, unlike, so then let's talk about the Galerkin method, which is slightly different from the least squares method, right. Unlike the least squares minimization technique and the collocation method which follows therefrom, which we have seen earlier, where the collocation method is just the discrete version of the least squares method, it is just the discrete version of the least squares method. The Galerkin method determines the coefficients using a different criteria. In the Galerkin method, the residual function, which is f minus sigma I equal to 1 to n ci my L psi I. Remember that we are constructing the best approximation to f using the basis functions psi I, right. So, L psi I linear combination of that is approximately equal to f, is required to be orthogonal to each and every member of Hn, right. This is different because in the least squares method, what did we see? This had to be orthogonal, this residual was orthogonal to each of the L psi i's, right. It is orthogonal to the linear operator operating on each of the psi i's, right. So, L psi 1, L psi 2, L psi 3, L psi m. So, residual is orthogonal to L psi i's, but in this case the residual has to be orthogonal to the basis functions themselves, right. So, it is orthogonal to each and every member of Hn. This imposes the restriction that this imposes the criterion that f minus sigma I equal to 1 to n ci L psi I comma psi j is equal to 0 for all psi j belonging to 0 to m. So, if I compare this with, let us see, with that, right, with that you can see the crucial difference is this is orthogonal to L psi j, that one in the Galerkin method it is orthogonal to psi j. In the least squares method, the residual is required to be orthogonal to each and every linearly independent component of the best approximation to f. It is, and which the best approximation to f is considered to be this, right. So, the residual must be orthogonal to each and every linearly independent component of the best approximation to f. Linearly independent component of best approximation to f are my L psi 1, L psi 2, L psi 3, right. So, this is by the definition of the least squares method, right. F must be orthogonal to each and every linearly independent component of the best approximation to f. That is why we have this criterion. That is why we have this criterion, right. While in the Galerkin method, this residual is required to be orthogonal to my basis functions, right, my basis functions for that function space, right. So, that is a very important point of difference, right. So, this is, so that is the basic difference between the Galerkin method and least squares minimization. In the Galerkin method, on the other hand, the residual is required to be orthogonal to each and every member of the space of functions Hn, and thus by extension to each and every basis function of Hn. That is, it is required to be orthogonal to each and every psi j, right. The Galerkin method and variations of it, such as the finite element method, are widely adopted in the numerical solution of partial differential equations. Why? Because the Galerkin method possesses something known as the best approximation property, right, and by extension, since the finite element method is also a Galerkin method, right, there are variations, but let us assume that. So, it is a Galerkin method, it also possesses the best approximation property. Recall that the operator L defined on a space Hn equipped with the inner product is said, this we have discussed when we were talking about partial differential equations. The operator L is self adjoint if LUV is equal to ULV, right, for all UV belonging to Hn. In addition, the operator L is positive definite if LU comma U is greater than 0 for all U belonging to Hn if U is not equal to 0, right. So, that if it is positive definite, that is true. assuming L is self adjoint as well as positive definite, we define a new norm, right, new norm associated with the operator L, right. And what is that new norm? The norm of uv, right, is an associated inner product, right. The norm depends on the inner product. So, the inner product uv is equal to u comma lv. It is no longer equal to my original inner product which I defined earlier, uv, right. So, now the inner product is with respect to this linear operator. So, this is a new inner product I define, and using this inner product I get this norm. So, u using this new definition of the inner product is u comma lu, right, and this norm is equal to the norm squared is equal to the inner product. So, this norm square is equal to that, right, because norm square we said is equal to the inner product. So, in this new definition of the norm, so every a function space has a certain inner product, a function space with an inner product, right, and the norm is always related to the inner product, right. The norm arises from that inner product, right. So, in this case the inner product is defined by that, and this gives rise to this norm, right, this norm u. So, norm of u, right, u is a member of that function space. If I am interested in the magnitude of u, in the norm of u, how am I going to evaluate the magnitude of the norm of u? I am going to take the inner product of u with itself, and now my inner product is different. It is no longer u dot u, it is u dot lu, and whatever I get there is the square of the norm of u, right, is the square of the norm of u. So, there is a one-to-one relationship between the norm and the inner product, right, norm vector space in a normed function space, right, the norm is related to the inner product in this way, right. So, the inner product, this inner product is distinct from the inner product associated with the L2 norm, right, inner product is, and it is defined with respect to the operator L, right. So, what is the best approximation property? The best approximation property is this: if my operator L is positive definite, meaning that it satisfies this property, right, it satisfies that property. If my operator L is positive definite and u star is the solution of my problem, right, my problem B, which was L u star is equal to f on D, L bar u star is equal to 0 on del D, right, and u star is the solution, is the true solution of the problem, then the Galerkin method always gives the best possible approximation to u star in the function space measured in this norm, right. Best approximation, as soon as you say it is the best approximation, you have to show in what norm it is the best approximation. How do you say it is the best approximation? You say it is the best approximation if your solution obtained in the Galerkin method that differs from the best solution. If you calculate the difference between the solution obtained using the Galerkin's method and the true solution in some norm, which norm is that? This norm which we have defined, that gives me the smallest possible norm, right. So, it is closest to the true solution in this norm, right, it is closest to the true solution in this norm. So, that is the property of the Galerkin. So, if we have a norm defined like this and we get the solution of a problem using Galerkin's method, right, that solution to the problem obtained using Galerkin's method differs from the exact solution, but the difference is minimum, the difference is minimum in that norm, right, in that norm, right. So, in that if you obtain the solution by some other method, for instance by the least squares method, and you calculate the difference in this norm, that difference will be larger than the solution you have got obtained using Galerkin's method, right. That difference will be larger than the solution you obtained using Galerkin. This is the property, this is the best approximation property of the Galerkin method, which passes on to the finite element method, and that is why the one reason why the finite element method is so widely adopted. From the solution of the error minimization problem, the best possible solution u in Hn, u must belong to Hn, right. It is the best possible solution that can be constructed from the basis functions used in Hn, right, must satisfy the requirement u minus u star comma v is equal to A0 for each and every v belong, but that is that we know, right. Solution of the error minimization problem, we know that the residual inner product v must be equal to 0 for each and every v belonging to Hn. However, v, if I evaluate that, right, u minus u star comma v, I take advantage of symmetry, write it like that, right, and that can be written as v l u minus u star, because this inner product means v comma l u minus u star, my usual inner product, right, my usual inner product, and that is equal to v comma lu minus v comma lu star, again taking advantage of the linearity of the operator, right. So, I get v comma lu minus v comma f, because lu star is the exact solution, u star is the exact solution, lu star has got to be equal to f. So, v comma lu minus v comma f, which I can write as v comma lu minus f. Thus, requiring v comma u minus u star is equal to 0 is equivalent to requiring v comma lu minus f is equal to 0. But v comma lu minus f is equal to 0 is nothing but the Galerkin condition, right, which we have seen, right. V comma lu minus f is equal to 0, that was my Galerkin condition, right, that was my Galerkin condition. If psi is v, right, if I think of psi as v and this is f minus lu, right, that is my Galerkin condition. So, to minimize the error, if I minimize the error, then I satisfy Galerkin's condition. To minimize the error, I have to satisfy that requirement, right, that I know from earlier, right. To minimize the error, I have to satisfy that requirement, and satisfying that requirement is equivalent to satisfying the Galerkin condition. Hence, finding the best possible solution u belonging to Hn in this norm is equivalent to finding the solution using the Galerkin's method. So, instead of finding the best possible solution to u in this norm, if I solve the equation using Galerkin's method, right, find the best solution using Galerkin's criterion, right, but basically find, reduce the ensure the approximation satisfies this criterion, the Galerkin's criterion, then I am going to also get my satisfy my best approximation property. It can be shown that the best approximation property of the Galerkin's criteria, it not only minimizes, it not only gives me satisfies that condition, it also minimizes a certain functional, right, which if I define that functional like this, it also minimizes that functional. What is the advantage of it? Why do we want to emphasize this, the fact that the Galerkin solution minimizes that functional? Well, we are going to see that later on, right. Actually, it can be shown that this functional can be written like this, u minus u star inner product of u minus u star minus inner product of u star. Why? Well, let us see how. Let us see, u minus u star inner product u minus u star, I can write it as u minus u star au minus au star by definition of the inner product, right. This I can write as u comma au minus u comma au star minus u star comma au plus u star comma au star, taking advantage of linearity, right. This becomes equal to u comma au minus u comma f, because a u star remember is the exact solution. So a u star is equal to f, u comma f, and again I have interchanged taking advantage of symmetry. I can write as a u no sorry, I have not interchanged. I have taken advantage of the fact that my operator is self adjoint, right. So a u star comma u, right, a u star comma u plus u star comma a u star, right. U star comma a u is equal to a u star comma u, because the operator a is a self adjoint operator, right. So this I can write as u comma a u minus u comma f minus a u star, I can again replace by f, minus f comma u plus u star comma u star, a u star. So this is equal to u comma a u, and again taking advantage of symmetry I can write f u as u f. So minus 2 f comma u plus u star in a product, right. U star comma a u star I can write as inner product of u star, because that is how I define my inner product, right. So you can see that inner product of u minus u minus u star minus inner product of u star is actually equal to u comma a u minus 2 f comma u, right. If u is equal to u star, that means if u is equal to the true solution, then this thing becomes 0. So this difference is minimized, right. U comma a u minus twice f comma u is minimized among all functions u for which the functional u a u minus 2 f u exists, because then it becomes 0, right. Since Galerkin's method gives the best approximation to u star in that norm, it also minimizes the above functional in Hn, right. Since Galerkin's method, we have seen that Galerkin's method gives me the best approximation to u star, right. Since Galerkin's method, so if I calculate u using Galerkin's method, I am assured that this difference is going to be a minimum, because Galerkin's method gives me the best approximation to u star. So this norm is going to be minimum, right. This norm is going to be minimum, that means that also gives me, it minimizes this functional, right. It minimizes, the Galerkin's method minimizes this functional, right. Why is that important? Well, we are just going to see. In many problems of mechanics, variational principles exist which lead to derivation of the governing equations of a problem by minimizing a functional, typically the energy functional associated with that problem. So I am able to write an expression for the energy, and by minimizing, by the variational principles which by minimizing that energy allow me to get the equations of motion, right. So we write an expression for the work, right, the principle of virtual work, for instance, right, principle of virtual work. So all that depends on this, right. I don't want to get too much into mechanics, but then we can write an expression for the energy, minimizing that you get the equations of motion. So the Galerkin method for self-adjoint operators L is thus a way to minimize the associated energy functional, because we are seeing that by when we solve a problem using the Galerkin's method, when we find the solution using Galerkin's method, we are also minimizing that potential, that functional, right, that functional like this. So when we are solving the problem using Galerkin's method, we are minimizing that potential. So if this potential of this function, I am always talking potential, but if this functional is the energy potential, right, it is the energy associated with that problem, I am also minimizing the energy, right, I am also minimizing the energy, right. So Galerkin's method for self-adjoint operators L is thus a way to minimize the associated energy functional if the energy functional can be expressed in the above form, and thus can be regarded as a variational method. The Galerkin method for self-adjoint operators can therefore be regarded as a variational method, because it leads to the same result, right, it leads to the same result. Is that clear? I think we will stop there and we will talk about weighted residual methods and specialize them to finite element methods in the next class.